This is part 1 of Unit 5, Lesson 2, Extrema on an Interval. So we're going to start with the topic of the extreme value theorem. We're going to discuss global versus local extrema, and we're going to formally introduce the idea of critical points in this section. So the maximum and minimum values are called the extreme values or extrema. The process of finding them is called optimization, and we've all done lots of optimization problems. We want to optimize profit. We want to optimize production so we have the least cost. So that's what we're looking for, the max or the mins. So there will be times when we want to find a max or a min on an entire domain or just on a particular interval. So we are going to learn in this section how we can do that without looking at a graphing calculator. So let's first define what a global or absolute extrema is. So if a function f on an interval, I'm sorry, I read that completely wrong. If f is a function on an interval I, then y equals f of c is the absolute or global maximum on I, if and only if f of c is greater than or equal to f of x for all x. And an absolute or global minimum on I is if and only if f of c is less than or equal to x for all x and I. So in other words, what this is saying is, you know it's the global maximum at a particular point c if its y value is the same or greater than every other y value on that domain or on that interval. And same for a minimum. It at some particular c, some particular x value on the interval, its y value, f of c, is the global minimum if its value is less than or equal to every other y value on that interval or domain. Okay, so looking at this graph, what we can see here is we have a closed interval, and we can determine the extrema on the domain. So first, our global max occurs here at point E. So here, right here, that's our f of E. Okay, and that's going to be our absolute maximum. Okay, so f of E is the absolute maximum. At x equals E. And then we also have an absolute minimum here at D. So here is f of D. So f of D is the absolute minimum. And that occurs at x equals D. Now we also have some relative extrema here. So here at this cusp right there, we can call that a relative minimum. And that, of course, is f of B. Right there. That occurs at point B. And then, of course, we have a relative maximum right here at point C. So there is a relative maximum. And that is f of C. And that occurs at C. Okay? So, defining relative and absolute extrema of a function. So relative or local extrema are the y values on the graph where the function changes from increasing or decreasing and vice versa. And that includes a cusp, like right here, or a corner or a pointy part, whatever you want to call it, because the function is going to change direction, even if the derivative doesn't exist there. And a global or absolute extrema is the highest or lowest value on a graph, on a specific domain, or in a specific interval. Now, a function does not have to have an absolute extrema. It may or may not. Okay, so relative extrema is defined in this way, relative or local extrema. If there's an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum. And if there's an open interval containing C for which f of C is a minimum, then f of C is called a relative minimum. Now, things to note here. First, when we say an open interval containing C, remember that since this is on an open interval, we are not including the endpoints. So C has to be between A and B. So the second notice says that is, C will be contained somewhere inside the interval and not on the endpoints. A relative extrema is slightly different than absolute extrema, and all is necessary for a point to be a relative min or max is for that point to be a maximum or minimum around the area of that X. So that's why it's relative, because it depends on how far away from that point you move. So depending, it might be a maximum in one little section of the graph, but if you use a larger interval, it may no longer be the relative maximum. So that's why it's called relative. And the last little noteworthy point is there can be smaller or larger values of functions at some other location, but relative to x of c, that f of c is smaller or larger than all the other values. So what we then create is what we call a neighborhood of c. And the size of that neighborhood is all dependent on how it's defined. Okay, so doing a couple of examples now. In many cases, we will be asked to analyze both open intervals and closed interval functions. So example 2 says, consider the graph of y equal to g of x shown at right. And so if you can see, this graph has all real numbers as its domain, so it is going to be an open interval analyzation. Okay, so we are to state the relative extrema of g of x, and then considering the domain, what are the absolute extrema? So relative extrema in this case are going to be any minimum or maximum. So we are talking about right here, there's a relative minimum. Right here, there's a relative minimum. Okay, so we have two relative minimums. And we have one relative maximum, and that would be right there. Now the question is, considering the domain of G, which is all real numbers, what are the absolute extrema? So what we notice is that since G is going to continue to increase, that it has no relative maximum. I'm sorry, no absolute maximum. What it does have is an absolute minimum right here at this point. So formalizing that, so the domain of G is all real numbers. There is no absolute maximum. But the absolute minimum is at that point -3, -8, because that is the lowest point on that graph. Okay, next, now we have a closed interval. Consider the graph of y equal to f of x, and we're only considering between 0 and 12. Now we're supposed to find the relative extrema, and then thinking about the domain, what are the absolute extrema? So relative extrema, I am just going to pick the ones that are actually relative. And when I do so, I only have one point, which is right here on my domain, which is going to be at x equals 10. So I have a relative minimum Okay, and then I have an absolute maximum. Because this is definitely the highest point between 0 and 12. And that is at 7, 7. And then I also have an absolute minimum. And that is here at that cusp. And that is at 2, negative 2. Okay, so what conditions would be necessary in order to have both an absolute maximum and an absolute minimum? Because that has to happen sometimes, but not all the time. So is there a way to determine that? So that is where our extreme value theorem comes from, our EVT. So these conditions have to be met, and you want to make sure that you remember them and include them on any question. So F is continuous on a closed interval. So then F has both a maximum value and a minimum value. It has to. If it's continuous, it has to have a highest point and a lowest point. So extreme values can occur at interior points or the endpoints of an interval. A function may have both max and min values over the interval, or it may have no extrema. So let's take a look at that. One thing to remember is that the fact that we have an if hypothesis is that if that condition is not met, either, and we have two conditions, we have our continuity and we have the closed interval. So if neither of those are met, there is no guarantee that we will have both a max and a min. However, it is possible for that to happen even if those guarantees don't happen. So just because it doesn't meet the conditions doesn't mean we don't have our absolute extrema. So here are 4 examples where we don't meet the conditions. Some of them have extrema, absolute extrema, some don't. So let's go through these. So for number 4, for each graph below, explicitly state where the hypothesis of the EVT fails on the interval 0 to 3, and then determine if the function has an extrema on the interval. Okay, well, A is pretty obvious here. We are discontinuous at x equals 1, so the EVT does not apply. Since f is not continuous on 0 to 3, the closed interval. But we do have extrema. We have an absolute minimum right here at x equals 0. And we also have an absolute maximum, which is right here at x equals 1. Okay, next problem. Similar idea here. We have another jump discontinuity, so the EVT does not apply. There's our closed interval, 0 to 3. But what you'll notice is our lowest point is a hole. So we don't have an absolute minimum. But we do have an absolute maximum here. So here we have one of the two, even though the conditions are not met. Okay, next. Now we have a vertical tangent line at 3. So the EVT does not apply. So again, f is not continuous. Whoops, I almost put is continuous. On our closed interval. So what's happening here? In this case, we have no extrema, because we're never going to have an absolute minimum, because that's going to continue to decrease. And the point where absolute maximum should be has a hole, so we don't have that either. Okay, so now, again, in letter D, our endpoints are not included. This is an open interval, so the EVT does not apply. And then we can look for extrema. And what we find is that we do have an absolute maximum and an absolute minimum. So our absolute max is at x equals 2. I'm sorry, x equals 1. And our absolute min is at x equals 2. Okay, so the extreme value gives us knowledge of when extrema occur, but how we find them algebraically when we don't have a graph like we were given in the last problem. So we are going to ask in the next video, how can we identify all the x values for the extrema occur? And there is a procedure for that. So stay tuned.